So in this video, we are going to see the Cayley-Hamilton theorem. So what it states is that for M finally generated A module and A an ideal of A, and also with having psi an A module endomorphism of M such that psi applied to M is a subset of the ideal A by the module M. Then psi satisfies the following equation, which is psi to the power of n plus A1 multiplied by psi to the power of n minus 1 plus a lot of other coefficients and terms, and plus an minus 1 psi to the power of 1 plus an, and this equals to 0, where all the A sub i's are elements of the ideal A. Now, to prove this, since we know that M is a finally generated A module, we can denote the generators by, let's say, M sub 1, M sub 2, M sub n. Those are the generators of M. Now, here we have that psi applied to M is a subset of AM. Thus, when we apply psi to any of those generators, we have an element belonging to the ideal the ideal A multiplied by the module M. And we know the shape of the elements in this ideal by module. So this is psi of M sub I equals the sum from j equals 1 to n of A sub I sub j multiplied by M sub j. And we have that A sub I j is an element of the ideal A. Now, this thing here, we have n different generators of M, so n different M sub i's. So if we unfold this, like if we write each of them, let's just write a few of them. What we have is psi of M1 equals A11 multiplied by M sub 1 plus A12 M sub 2 plus etc. till A1n multiplied by Mn. Then for M2, we have A11 M1 plus A12, sorry, this is a number 2 and this is a number 2, multiplied by M2 plus etc. till A sub 2 n multiplied by Mn, along the way till psi of Mn, which is equal to A sub n1 multiplied by m1 plus etc. till a sub nn multiplied by mn. And we have n of those, which each of them have n terms. Now, we can rearrange this, and it's basically moving this psi of m sub I to the other side. So that then what we would have is, I will put it here on the right, we would have psi of m1 minus all the things on the right, which is a11, m1 plus blah 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 plus a1n mn, and this equals to 0 till the last one, which is psi of mn minus then a sub n1 m1 plus etc. till a sub nn multiplied by mn, and this equals 0. Now the idea here is that we can group all the terms that have m sub I for each row I. So at the first row we group all the terms which have m sub 1. At the second row all the terms who have m sub 2. And at the n row here we group all the terms who have m sub n, which is this thing and this thing. Let's do it here. So for example, for the first row at I equals 1, we can group psi minus a11, and all of this is multiplied by m1. And now we continue with the rest of things. So it's like subtracting a sub 1, 2 by m2 minus etc. till minus a sub 1 n multiplied by mn, and this is equal to 0. Now at I2 what we have is, so the first term will be minus a sub 2 1 multiplied by m1, but then for the second term we group with the psi, so we have plus psi minus a2 2 multiplied by m2, and it goes on till a sub 2n multiplied by mn. This equals 0. This goes on till I equals n. And here what we will have is like minus a n1 m1 plus, well actually it's like a minus, all the other things till we reach the last one, which is like psi minus a n n multiplied by mn, and this equals to 0. So now this is more interesting. You can notice that at each row, at the term I, we will not have like a usual thing, but we will have this like parenthesis with psi minus a sub I. And this is like this diagonal. So let's represent this as a matrix, which will be quite useful. So we will have psi minus a11, and then minus a12, etc., minus a1n. Now for the second row, we have minus a21. Now here we have psi minus a22 till minus a2n, till we reach the last row, which is a minus a sub n1 minus a sub n2 till, well, here we have psi minus a n n. So this is our matrix, which is being multiplied by all the m's, and these m's in the matrix representation, we can have them as a vector of m's, m1, m2, etc. till mn. Those are the generators. And this equals to the vector 0, which is what we have here on the right. Now, let's call this matrix big high. This is like the vector of generators of the module M, and this is like the 0 vector. So what we have here is actually psi multiplied by M equals 0. Now let's continue on the following page. So what we have here, again, okay, I will write this last equation. Psi multiplied by M equals 0. Now, small parentheses. So we know that that there is this equation from the fundamental identity for the adjugate matrix, which states that the adjoint of the matrix psi multiplied by the matrix psi itself equals the determinant of psi multiplied by the identity matrix, like the diagonal matrix. This is the fundamental identity for the adjugate matrix. So let's apply this to our previous equation. So we are going to multiply both sides by the adjugate. So what we have is adjugate of psi multiplied by M equals the adjugate of psi multiplied by 0. This just goes to 0. And what we have is this thing. Notice that adjugate of the matrix multiplied by the matrix equals to the determinant of the matrix multiplied by the identity matrix. So this is the determinant of psi multiplied by the identity matrix multiplied by M. And this equals to 0. Now, this has the shape of like, it's something like determinant of this, all the rest are just zeros, and just like the diagonal has the value of the determinant. Is 0, 0, 0, and then what we have here is that this will be M1, M2 till Mn, and this is equal to 0, 0, and well, the vector of zeros. So if you apply this operation, what you have is that at each multiplication, at each like step of this multiplication, you can just say that you have the determinant of the matrix psi multiplied by, at each step you have a different m sub I, and this equals to 0. And this goes for all I in the range of n, like from 0 to n, well, from 1 to n, sorry, n, yeah, to n. So what we see here is that the determinant of this matrix, of the previous matrix, like the psi, is what we call the annihilator of m sub i's, which are those are the generators of the module M. So let's write it. So the determinant of psi is the annihilator of m sub I for all I in the range of n, and this means that is the annihilator of the entire module M. So we are interested into computing and calculating this determinant. Now, in order to compute the determinant, we will use the Leibniz formula, and it's like a typical high school approach, just like diagonal, and then these like weird diagonals and so on. The thing here is that it will have some shape like, let's write it. This is the determinant of psi equals to, sorry, not so we want the determinant not of this matrix, but of psi. Let's maybe first put psi here into the notes. So recall, psi had this shape of c minus a sub 1 1, a sub 1 2 till minus a sub 1 n, a sub 2 1, psi minus a to 2, a to n, then minus a n 1 till psi minus a n n, so that we had this like diagonal where it's like psi minus a I. So in order to do the determinant of psi, this is psi, we would have like a multiplication of all those terms, like psi minus a 1 1, psi minus a 2 2 till psi minus a n n. And then here we would continue adding other things like minus a sub n multiplied by blah blah blah. But the thing is that we know that all those terms would have the coefficients. So all the a sub ij combinations will be in the ideal. So combining all those things, the coefficients will be in the ideal. And then combining all those things, all the operations that involve psi will not be bigger than psi to the power of n. So as a result, we would have, so the highest power is, it will be coming from here, which is like the term that has more psi's being multiplied between them. So here the max, the highest power will be 1 multiplied by psi to the n. And then for the rest of psi to the k, we will have here some a sub I, and this a sub I is a member of the ideal. So then what we will have is something like determinant of psi is equal to, well, we know that is like, it comes from a product of psi minus a I, and then minus some other thing, and this will be equal to the following equation, which is like psi to the power of n plus a sub 1, and a sub 1 is like an element of the ideal A, multiplied by psi to the power of n minus 1 plus a sub 2, multiplied by psi to the power of n minus 2 plus etc. plus a sub n minus 1 multiplied by psi plus a sub n. So this is the determinant. Now, the thing here is that what we had earlier is this equation. I will write it down. So we have determinant of psi, which now we know that is this equation, multiplied by I multiplied by m equals 0. And then we saw that since this is like the diagonal, like the identity matrix, this is the same as saying that determinant of psi multiplied by m sub I, like each of the generators at each time, equals 0 for all the I in the range of n. Now, the thing is that this psi is what it's called the characteristic matrix. And so psi is a characteristic matrix, which is also written as m sub I minus a. So what we have is that the determinant of psi, it should be also the determinant of m multiplied by I minus a. And this is what, so this is the characteristic matrix. And this is, we can denote this as this polynomial. Sorry, this is like an x. So this is the polynomial p of x, and this is the characteristic polynomial. Now, the thing is that this matrix built as an operator is what we are using. It's an operator where we have this like psi, which is like an A module endomorphism. Now, if a linear transformation turns every basis vector, which is like the m sub I, into 0, then that transformation is the 0 transformation. So in our case, the determinant of psi is the 0 transformation. Now, therefore, what we have is that the determinant of psi, seen as an operator, is the 0 transformation. So what we can write is that this equation, which is the determinant, equals to 0. So that we have what we had at the statement of the Cayley-Hamilton theorem. So that psi to the power of n plus a sub 1 multiplied by psi to the power of n minus 1 plus all the way till a sub n minus 1 multiplied by psi plus a sub n, this is equal to 0. And this is what we had as the statement of the Cayley-Hamilton theorem. So that we have proved it. Now, once we have this theorem proved, we can use it for a corollary. So let's go for that. Now, this is the corollary of the Cayley-Hamilton theorem. And it states that for m finally generated A module, A an ideal of A, such that A m equals m, then there exists some x which is equivalent or congruent to 1 modulus the ideal A, such that xm equals 0. So let's prove this. And for this, we're going to use the Cayley-Hamilton equation, like from their theorem. And where we have psi, we are going to assign the identity of m to the Cayley-Hamilton theorem. So recall we had this psi to the power of n plus a sub 1 psi to the power of n minus 1 plus till the way to a sub n minus 1 psi plus a sub n equals 0. So we're going to here to use the ID of m instead of psi. And when you have the identity and you apply it n times or n minus 1 times, you still get the identity. So this is the same as saying this ID of m plus a1, ID of m plus blah, 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 till a sub n minus 1, ID of m plus a sub n equals 0. Now let's group all those ID terms. So we have here 1 plus a1 plus till a sub n minus 1 plus a sub n. Notice that here having a sub n is the same as having a sub n multiplied by ID m. So that's why it's like we have this thing here. So all this stuff multiplied by ID sub m, this equals to 0. So also notice that if you have ID of m of some m, and here m is a member of the module m, this will again be m. So if we apply this equation to m being an element of the module m, what we will have is 1 plus a1 plus etc. till a sub n multiplied by ID m of m, which this is the same as saying m. And all the a sub i's are elements of the ideal A. Now, if we denote this by x, what we have is that x multiplied by m equals 0 for all m's in m, which is as if we say that x multiplied by the entire module equals 0. This is what we had here at the statement of the corollary. So this is like one part, and then the other observation is that we are given that there exists this thing. Let's see how this exists. So having x congruent to 1 modulus alpha, the ideal A, well, this x congruent 1 modulus the ideal A, this is as saying that x minus 1 is an element of the ideal A. So we know that, so we had here earlier that x equals 1 plus a1 plus till a sub n. Denote this by b. What we have here then is 1 plus b. Then if we take this thing here, it is like x minus 1. This is the same as saying 1 plus b minus 1. Both ones cancel, and this is the same as saying b. Now, we know that all those a sub i's are in the ideal A. So this is in the ideal A, thus x minus 1 is in the ideal A. So x minus 1 is in the ideal A. Thus x is congruent to 1 when applying the modulus of the ideal A. And we are done with the proof. Now, the next thing that comes naturally after this is what's called the Nakayama theorem. Let's see what it's about. Sorry, the Nakayama's lemma. So Nakayama's lemma states that for some m, a finally generated a module, and then the ideal A, which is an ideal of A, such that A is an element of the Jacobson radicals of A, then A m equals m implies that m equals 0. So, to prove this, by the previous corollary, we had, so this is by the corollary of the Cayley-Hamilton theorem, we had that if am equals m, then xm equals 0 for some x which is congruent to 1 modulus the ideal A. And this was as saying that x minus 1 is an element of the ideal A. Also, another thing to recall is that we have this theorem that says that if x is an element of the Jacobson radical of A, this happens if and only if 1 minus xy is a unit in A for all y in A. So we're going to use this, and so since this happens, like since x minus 1 is an element of this ideal, this means that x minus 1 is an element of the Jacobson radical of A, because A is an ideal which is like a member or a subset of the Jacobson radicals of A. So then we have this thing here, and you can see that this is quite similar to this. So we have that x minus 1 is an element of the Jacobson radicals of A, if and only if there is this. So since we know that this is a fact, because we deduce it from, well, this is given by the hypothesis, we know then for sure that there is this thing that is like 1 minus xy, and here this x is not actually this x is x minus 1 multiplied by y. This is a unit in A for all y in A. And this, we can just like cancel things out and so on. But the main idea will be that x is a unit. So actually this is like 1 minus xy minus y, which is 1 plus y minus xy. So since x is a unit, we know that x minus 1 multiplied by x equals 1. So when we have m, we can multiply it by 1, which is the same as saying x minus 1 plus x. X minus 1 multiplied by x multiplied by m. And then from the previous corollary, we had that this is 0. This is what we had here. So we know then that this is 0. So that the m is equal to 0, as stated in the Nakayama's lemma hypothesis. So this is proven. Now, once we know the Nakayama's lemma, then there is a corollary that we can also conclude, which states that for, again, M, a finally generated a module, let N be a submodule of M, and again, A, an ideal, which is like a Jacobson radical of A, so it's an ideal. Then, having M equals to AM plus N implies that M is equal to N. So let's prove this. The idea is to apply Nakayama's lemma to the quotient of modules M sub N. This is the idea. So let's start. Since M is finally generated, then we know that M quotiented by N is also finally generated, and also it will be an A module. Since the ideal A is a Jacobson radical, then Nakayama's applies to M N also. So, by definition, we know that the ideal A multiplied by M, the module M, will have the following shape, which is like a summation of A sub I multiplied by M sub I, where A sub I are elements of the ideal A, and M sub I are elements of M, which actually they are the generators of the module M. Now, we are interested into the same thing, but instead of M, with the quotient M quotiented by N. So A multiplied by M quotiented by N, this will be the sum of A sub I, multiplied by M sub I plus N. This is like the shape of this quotient, like all those cosets. And here we have A sub I, again, members of the ideal A, and M sub I are the generators also of M. Now observe that here, if we have A sub I multiplied by M sub I plus N, we can distribute this and we will have A sub I multiplied by M sub I plus N. So all this thing is the same as writing A sub I multiplied by M sub I plus, so all this goes inside, plus N. And here, this side here, this belongs to AM. So the entire thing belongs to AM plus N. So let's turn the page. What we, not turn, but like starting a page. What we have then is that a of the multiplied by the quotient m by n, this will be, I will write again what we had until now in the previous page. So we had the summation of a sub I m sub I plus n, and here we have a sub I being a member of the ideal A, and m sub I generators of m. This is, as we saw, saying a of m, a multiplied by m plus n, because this is the ideal A multiplied by m. So then this is a m plus n. So this is the same as saying the following shape, which is x plus n, where x is an element of a m. So that this is a m plus n. Now, if we take a sub m, a multiplied by m plus n, and we quotient it by n, what we will have is some y plus n, is like the shape, and this y is an element of a m plus n. But notice that this is the same as, so it's like having something which is n plus n. So it's like you can just have a simple n. So this is again a multiplied by m plus n. So this thing equals to this thing, which actually this thing is the same, and this equals to this thing. So this thing equals to this thing. Now, from here we can conclude that this thing, a m plus n quotiented by n, equals to this thing, which is like x plus n, where each x is a member of the ideal A multiplied by m. So, long story short, what we have is the ideal A by the quotient mn is the same as the ideal A multiplied by m plus n, which is the same as the ideal A multiplied by m plus n divided by quotiented by n. And from the corollary, we had that, in the assumption, we had that m equals a m plus n. So quotient this by n. So we have m divided by n equals a m plus n divided by n, which is what we have here. So this is also m divided by n. So we have this thing here as like this is like the TLDR of the entire thing. So what we have is that a of this multiplied by this quotient equals to the quotient itself. Now, by the Nakayama's lemma, recall Nakayama well, I have it actually here. So by the Nakayama's lemma, what we had is that if you have a m equals m, this implies that m is 0. We'll write it here. So if you have a m equals m, this implies that m is 0. So here, what we have is that a by this quotient equals this quotient. So by Nakayama's lemma, what we have is that this quotient is actually 0. So this quotient now has the shape of m plus n, where m is an element of, well, it's like generators of m. And this is equals to 0. So this means that the 0 element in M quotient n is the coset n equals 0 plus n. So this means that this quotient, since actually forget about this, since this quotient is equal to 0, this means that this quotient can only have one element, which is the 0 coset of n. So what we have here is that for all m, we have that m plus n equals 0. What this means is that m plus n equals the 0 coset, which is the same as saying 0 plus n instead of m. This is the same as saying that m minus 0 is an element of n, which is the same as saying that m is an element of n. So, for all m, it belongs to n. And from the assumption of the corollary, we had that n is a subset of m. So I will write this here. N was a subset of m. Now, having that all the m's are elements in n, this is the same as saying that m is a subset of n. So what we have here, we have n a subset of m, and m a subset equal to of n. So those two things mean that m equals n. And this is exactly what we had here at the hypothesis of the corollary of the Nakayama's lemma. So we are done with the proof. That's it. So in this video, what we've seen is first, let's put a bit of ordering. So first we have seen the Cayley-Hamilton theorem, which states that when we have this psi being an A-module endomorphism of M, such that psi of M is a subset of AM, then we have this equation being equal to 0, where all the coefficients of the terms are elements of the ideal A. To do so, we went over all those like matrices with this diagonal shape, so that we could eventually prove that this holds true. Now, once we have this Cayley-Hamilton theorem, we can then do this corollary, where we see that if there is this ideal such that AM equals M, then there exists this element X congruent to 1 modulus A, such that XM equals 0. This was quite short, actually. Then, once we have this, we went for the Nakayama's lemma, which basically it says that if you have this AM equals M, this implies that M equals 0. And then the corollary after Nakayama's lemma is that if we have N being a submodule of M, and then this means that when you have M equals AM plus N, this implies that M equals N. And this is what we just did here at the end. So that's it.